Well, hello, everyone, and welcome to the Here Exposomics webinar. Today's talk is on climate change and exposomics, presented by Dr. Eli Klug. Just before we start, I wanted to note a couple things. We will have time for some discussion after the end of the talk, so if you could please use the Q&A feature to leave any questions or comments, that would be appreciated. So we are pleased to have Dr. Eli Klug join us today for his talk, Climate Change and Exposomics, New Advances in Satellite-Based Exposure Modeling for Generating External Exposome Exposures. Dr. Klug is a professor of environmental medicine and climate science at the Icahn School of Medicine at Mount Sinai. He is an exposure scientist and GIS specialist. His research has focused on the development of novel geospatial methods for developing exposure models for epidemiologic studies, and his research has extended spatial temporal resolution of particulate matter exposure assessments and extreme temperatures. So with that, Dr. Klug, I thank you for joining us, and I turn it over to you.
Thank you very much. Share my slides. So thank you again for the invitation. It's an honor to present here, and I'll talk mostly about climate change and exposomic, but really focus on the new advances in satellite-based exposure modeling for generating external exposome exposures. And I'll focus the talk, or I'll split the talk into 4 parts. I'll start with an introduction to satellite-based modeling in general, specifically for environmental epidemiology. Then I'll transition over to one aspect of climate change, which is air pollution, and talk about some of the new advances in PM2.5 and PM10 air pollution modeling, giving an overview of where we started and where we are now. Then shift over to talk about new advances in spatiotemporal air temperature modeling, again, kind of going through the beginning and where we are now. And if I have time, discuss some of the geospatial built environment modeling that we do in my lab. So I'll start with introducing the field of exposure assessment, specifically satellite-based modeling for environmental epidemiology. And I assume it's practically clear to people attending this webinar, but why do we actually model air pollution and temperature for these studies? So we know that there's extensive literature on PM2.5 associations with health outcome, including hospital admissions, mortality, reduced birth weights, cardiovascular disease, respiratory disease, and of course, heart attacks and strokes and so on. And we've published in our group a lot on this topic. Likewise, to the extensive literature on the association of air pollution and health outcomes, we now see that changes in climate will lead to warmer temperatures and more extreme weather events, which of course are also associated with increased morbidity and mortality, specifically, and this is a key point, in sensitive populations. Now, it's also important to identify that this increase happens not only during heat waves, but we also have seen that during less extreme heat events, we also see these associations. So a bit about modeling PM and temperature and other environmental exposures. Traditionally, there's several modeling approaches that allow us to assess these exposures for health outcome studies. Some of them are more robust, some of them are more antiquated, but in general, if I had to kind of give an overview, we're talking about different model types, the classic proximity-based assessment methods where we take the distance to a major roadway or a point source emission, statistical interpolation methods that we can use modern networks for, such as IDW or kriging or bilinear interpolations. And then kind of getting more advanced, we've seen in the last 15, 20 years, advances in modeling using land use regression models where we can apply different spatiotemporal predictors to have a more robust method of assessing exposure. We have line dispersion models, CTMs, but really, us and many other groups across the globe have kind of moved towards these hybrid models. And in recent years, applying even more advanced machine learning techniques. And that's really going to be the focus of this talk. And the reason that we move towards using these advanced methodologies or hybrid methodologies is that we've encountered many modeling limitations in the past. So one of the limitations, or some of the limitations of these models is, they tended to use large geographical areas, such as a state or a nationwide extent, thus potentially biasing the health effect risk estimates due to exposure measurement error. And most of these methods focus on urban areas, which is natural because A, that's where monitors are placed. If you think about New York or Boston or LA, and you think about the density of monitors in these areas compared to the rural regions of these areas, that's always the case where we have a much higher density of monitors in the cities. And also, the bulk of the population, of course, is concentrated into these urban areas. So to address these limitations and allow us to kind of, assess exposures across CONUS, across the continental United States or other large regions of the world, we began developing these novel hybrid approaches. And the main driver behind that is that we started using satellite data, remote sensing data. The broad spatial coverage enabled by satellites allows us to expand our exposure data far beyond the range of the conventional ground monitoring networks that we've used in the past, allowing us again to penetrate both rural and suburban areas, covering much larger extents. And this allows us to greatly enhance our ability to estimate subject-specific exposure, no matter where the subject lives. Now, these satellite measures collected daily with very fine spatial resolution can help us robustly reconstruct both the spatial and the temporal patterns of exposures. Finally, obviously, there's a lot of advantages with satellite, but some disadvantages. So obviously, the main advantage I mentioned is the spatial coverage, right? We can cover an entire continent, entire nation. We can survey areas with very limited ground access because we're kind of, using data from space, and it's very economic. We have one sensor for the whole globe, but we have some limitations that we had to account for in our modeling. First of all, data availability, right? If there's snow, if there's dust, if it's in the nighttime, there is no satellite data, for example, for products that allow us to predict air pollution. We don't have a vertical profile, right? We get this kind of column data set, and we're interested in what people are breathing or exposed to at the ground level. And obviously, we have very different spatial temporal scales and extents from different satellites. So to address these limitations, we started looking at how can we use both remote sensing data, but other geospatial algorithms or methods that both are available and both that we developed in our lab to allow us to more robustly reconstruct air pollution exposures. And the main satellite that we've been using up until recent years was MODIS, the Moderate Resolution Imaging Spectroradiometer. And it is a payload scientific instrument launched by NASA in 1999, but actually data only starts in 2000. There's another satellite in the MODIS ecosystem called Aqua that was launched in 2002. Terra was launched, as I said, in 1999. And these instrument captures data in 36 spectral bands at varying spatial resolutions. We don't use all the spectral bands, but among the main products that we used is MODIS AOD, aerosol optical depth, and LST, which is land surface temperature, which we'll touch a bit later. This is an example of how the actual image looks. So this is what the MODIS satellite observed when it kind of overpasses. I forgot to mention that MODIS is a sun-synchronous satellite, which means that it circles the globe once every 24 hours. And then it provides data in tiles. So, this kind of rectangular image that you see is one tile of an overpass of MODIS. And then we can work with our NASA colleagues to get actual data, in this case, aerosol optical depth, and It's important to note that there's different algorithms to retrieve, aerosols from Otis. There's the dark target algorithm, which is better over oceans, and darkly or dark surfaces. Deep blue, which is better over deserts and light colored surfaces, such as the Sahara. But we have really focused on, and we have a long-standing collaboration with MIAC. The PI of MIAC is Alexei Yapustin, which really takes the advantages of both dark target and deep blue and creates a better, to our opinion, algorithm that is also higher in terms of the spatial resolution. And that's the main algorithm that we use when we process AOD data. So MIAC is the multi-angle implementation of atmospheric correction. As I said, it's an algorithm developed to kind of build on the strength of the different available MODIS algorithms. And one of the major improvements is that it has a much higher spatial resolution compared to the other MODIS dark blue and algorithm. It provides a 1 kilometer spatial resolution. Here you can see the different tiles of the MODIS data sets. So aerosol optical depth, or aerosol optical thickness, sometimes it's referred to, really measures the light extinction by aerosol scattering and its absorption in the atmospheric column. The satellite kind of looks at the changes in intensity of light, and based on that, it creates or produces a value. AOD is a unitless value. So if you look at, India, which is kind of in this area, semi-polluted, we're going to look at AOD values of 0.4 to 0.5. If there's a cloud across, then you're going to look at very high AOD levels. We always exclude these types of data when we clean the AOD data. And a normal AOD day or a clean day would show values of 0.1 to 0.2. So now that you know kind of what we're using from the remote sensing sources, let's discuss the methodology. So how do we actually convert or use, rather, the satellite data to actually get at what people are breathing on the ground? So this is an example of a AOD, a daily, 1 day of AOD data from both from MODIS and using the MIAC algorithm that we process through the use of geospatial software. We use R and QGIS, and you can see the scene over the Northeast. You can see kind of New York and Boston. You can see the higher or warmer colors denoting higher levels of AOD, and you can also see something very interesting. Not interesting for us, that a lot of the scene is missing. That's one of the challenges, as I said, with satellite data, that the vast majority of the data is missing due to cloud, due to snow, due to rain. There's various reasons why this happens, and we need to accommodate that in our modeling, and I'll soon show you how we do that. So AOD satellite data are spatial and temporally linked to our station data. So we have a series of kind of spatial temporal linking processes that connects the AOD or the satellite data with the station data coming from EPA and other sources of ground monitor data. In addition, as I said, because the satellite data comes as a column and we're interested in what people are breathing, we need to calibrate the data. So we add additional spatial and temporal variables to the AOD PM dataset using various geoprocesses and various raster functions, both in RJS, Python, and R. So these are the different layers that we overlay the remote sensing monitor data. In essence, the process started this way, but it's not changed very much, even though now we're kind of including much more sophisticated models, which I'll touch in a few minutes. But there's, a bunch of stages. First and foremost is the calibration stage, where we fit a calibration using the PM-AOD relationship plus additional spatial temporal predictors. Once we have that, we can go for every data point that we don't have monitoring stations, but we do have satellite data and predict there. And then the third stage is where we take, that relationship using, again, different geospatial methods and can even account for days that we don't have AOD data, as you've seen, and predict in these areas. And then we have additional stages. We have what we call a local stage, where we take the residuals from that process and we regress that versus very localized predictors to get at sub 1 kilometer predictions. In mathematical form, to whoever is interested, this is kind of a brief overview of how this is denoted. So it doesn't matter, if we're using linear or mixed effect models or machine learning approaches or Gaussian Markov approaches. We have the calibration stage that I've shown you. We have the prediction stage, which again changes, now that we've kind of moved over to using these sophisticated machine learning algorithms. And we have the localized stage on the residuals. So, we started with these models in 2010, 2011, and, we've seen that they produced pretty robust exposure assessments, and we've used it in many publications today. I'm going to show you some metrics of performance. So, these are the initial models, which we published, I think, in 2013 or 2014, covering New England and the Mid-Atlantic. Again, you can see these are cross-validated results, showing very good prediction performance. We then kind of looked at other regions of the world and this time PM10, and again saw very similar results. And this is kind of the main 2014 analysis where we expanded it across the Northeast. So this is an example of mean PM2.5 concentrations in each 1 by 1 kilometer grid across Boston. This is for 2003 in this specific case. And you can see the variability that we're able to capture between the urban core of the city and the rural areas. You can see that the model even captures roads that go in and out the major cities. And we have these models running daily. So for every day you get, a similar kind of surface generating predictions at these 1 by 1 kilometer grid cells. This is an example of the local stage where we take the residuals again and have a separate regression where we're predicting at a 100-meter level, in this case 200-meter level, and you can see that the variability across Boston, and I even overlaid the point source emissions so you can see how the model is able to capture that as well. In terms of prediction accuracy, again, the model from 2014 did very well, and that's all fantastic. And I'm an exposure scientist. As much as we have a great time developing these, I mean, the main purpose is using these types of models in environmental epi studies. So this is an example of a paper that we published looking on short-term effects of particle or PM exposure on hospital admissions across the Mid-Atlantic. As we've discussed, many studies report significant associations between PM2.5 and specifically, in this case, hospital admissions. But these studies mostly rely on a very limited number of monitors, which introduces exposure error and more critically excludes rural and suburban populations from location where monitors are not available, which ends up reducing generalizability and potentially creating selection bias. Now, when you have a spatiotemporally resolved model like ours or other groups that are kind of working in the same space, you can really start investigating, the entire population, but also look at both short-term effects of PM2.5 exposures and, long-term acute effects, depending on your research question. In this case, we looked at acute effects of PM2.5 exposures on hospital admissions in the elderly population across the Mid-Atlantic region. And this is an example of, a map of that region that we looked at, where I put the monitoring stations across, denoted with these black flags, and I created a buffer of 30 kilometers across these monitors. Now, even using 30-kilometer grids to assign exposure for people living in these buffers from the monitor, we know these days is not that great and creates a lot of exposure error. But even if you did that, you'd still lose a lot of the rural areas, like a big chunk of the population. by using a spatially temporally resolved model, you can include the entire population and robustly assess their exposure and reconstruct it going backwards. So these are, we can take these predictions daily and go back these days, 25 years now, on a daily level and tell you what the exposure was for participant, X to Z. So in this case, again, we assign exposure and we use a case crossover analysis for each admission type, matching on day of the week, month and year, and define the hazard period as lag 0, 1, which is the moving average of the day of admission and the previous day of exposure. I'm sure people know here the case crossover methodology where people are both their case and control. And then we saw significant increases in both all respiratory, CVD, stroke, COPD, and HID increase in admissions for a 10 microgram increase in PM2.5 exposure. So that's great. And, immediately after we kind of finished modeling large areas in the US, we thought that's fantastic. The satellites, as I mentioned, are sun synchronous, they're global. We have the same data across different regions of the world. Let's look at other regions. I thought it would be very easy, but I was very wrong because unfortunately, there is no one-size-fits-all approach. In each region that we extended our models, and I'll show some examples, each kind of region or geo region has very different characteristics and presents very unique challenges, such as we have snow in Northern Europe, we have dust storms in Israel, we have very humid climates in Mexico and India. So each model has to be adjusted very differently, and indeed up until now when we go and try to run these models in different regions, the models look very different from one another. For example, in Mexico we have issues with precipitation, we have issues with the planetary boundary layer, the PBL, which is very low, and Mexico City specifically when we model sits in this crater-like area, which creates a pressure cooker effect for the particles. They have nowhere to escape. We have very strong wind regimes. And in Israel, for example, where we model, we have very bright surfaces. So we had we have a lot of issues with the actual AOD algorithm, and we had to go back and forth with our collaborators in NASA to adjust for that. We have issues with sandstorms. How to differentiate, anthropogenic and non-anthropogenic particles? How do we deal with salinity from the sea? And how do we deal with much higher annual PM10 levels and the ratio between PM2.5 and PM10? So as you can see, there's very different challenges in every different region. Here's an example of the Israeli model. As you can see, it's going to be quite different from the US-based models. We have issues with sandstorms. This is an example of a day in the winter where you're hit from sandstorms, and sand can come from different areas. Sand can come from North Africa, pass over the Nile, and then the toxicants coating the sand particles are going to be very different than sand coming from Saudi Arabia, which would be much cleaner and have less health effects. So, to deal with that, we even had to develop our own dust classification algorithm to identify whether we're having a dust day or not having a dust day. And this is an example of a PM10 model in Israel and a PM2.5 model. And again, performance was very good in that region. In Mexico City, this was work led by Professor Alan Just, now Brown, that I was a collaborator on. Again, we had very different challenges in Mexico City, and this is the final result of years of work modeling PM2.5 in Mexico City. We have run ever since these models in different areas such as France and Switzerland and India, and then we kind of in 2018 thought about can we go sub-daily for PM2.5? We have different overpasses of the satellites. Should that be something of interest? My rationale over that was that, during the early mornings where we have the Terra satellite overpassing, we have much more anthropogenic activity. The PBL is much lower. So a lot of the particles should be attributed to anthropogenic activity and traffic, as opposed to the overpass of Aqua during the afternoon or noon, depending on the region, where the the PBL is higher. We have much more kind of long range transported particles coming in, and then the particle composition should be very different. So indeed, we did that data. We did observe different spatial patterns of the mean PM for non-dust period compared to the dust period days that we identified, and this allowed us to use these two different exposures, the anthropogenic versus what we call the background particles in health studies, as two distinct exposures. Even though we're very excited about that, a lot of our epi colleagues said that this is great, but it's very hard to get hourly or kind of diurnal health outcome data. So that's something that we still kind of haven't explored yet. And performance of the model was also very, very good. And here you can see the differences in actual PM levels and the spatial variability of that between the different hours of the day. Then another thing that we kind of looked at is can we use these new machine learning techniques to improve even further on the model? So this is something that we started in Italy, where we had some new innovations. One of them was kind of dealing with that missingness in satellite data, where we developed a random forest, a machine learning algorithm to allow us to create these surfaces of satellite data to address the issue of missing satellite data. And then we had the normal kind of approach of calibration, prediction, and going deeper in terms of the spatial resolution. And the idea was that each modeling approach that we can use, whether it's random forest or gradient boosting, has its own biases and limitations, and using an ensemble model to incorporate these different predictions from the different models with the different biases will outperform a single model approach. So this is the first time we kind of explored this ensemble method, where we looked at linear mixed effect models, a random forest approach, gradient boosting, and a CTM model. And then we used GAM to ensemble these different predictions. The reason that we use GAM is that this will allow the different predictions to move both over space and time as we put the different predictions from the different models. So this is a kind of a schematic view of how we do that. We take the different AOD PM data sets and the land use data, and we impute first the satellite MIAC data, and then we have 4 different learners: gradient boosting, linear mixed model, and random forest. I'm kind of borrowing from my kids. These are the Avengers basically, and different models. We get different estimations, and then we ensemble that using GAN, which will produce better all over PM 2.5 estimations. And we've shown that this indeed does help improve overall estimations compared to the single modeling approach that we've used in the past. And this is the kind of spatial representation of these predictions, looking at the different models by themselves. You can see the chemical transport model that we kind of included just to show kind of the limitations of such models that I discussed in the beginning of the presentation, as opposed to the more sophisticated satellite-based approaches, and of course the overall GAN predictions. Following that, we explored additional kind of methods to improve further. One of the things that we looked at is using Gaussian Markov random fields. GRF is a common statistical approach for analysis of spatial-temporal dependency over continuous domains. But the issue is that it's very computational inefficient. Our approach in this case for avoiding the computational hurdle of GRF is to add a Markov component or property. The Markov property induces conditional independence between the random variables. So a data point in GMRF depends only on its space-time neighbors, greatly improving performance. And the reason that we were excited about this approach that this allows us to predict much better in these rural areas that I showed you, which are far away from monitors, not concentrated in cities as compared to the traditional approaches. And we've shown that by using the GMRF approach, our model RMSE or prediction root mean square error decreases the farther away we go to the monitor compared to the classic approaches. Finally, regarding air pollution, we looked at Mall in France recently, and we had many challenges there. So we applied some new ideas. One of the issues that we had was, monitor sparsity. In France, there's a lot of PM10 stations, but relatively few PM2.5 stations. So we developed a machine learning approach to run a calibration in co-located PM10 and PM2.5 stations, allowing us to impute PM2.5 stations, greatly extending our monitoring coverage. That was the first challenge. And as you can see, we're doing a great job in imputing those PM2.5 stations. Another challenge, as I mentioned, was the gaps in satellite AOD. So again, we applied our imputation methods, running a gap-filled stage using a machine learning approach and reanalysis data, global reanalysis data that allows us to impute and fill in the gaps in the satellite data to create full surfaces. And then obviously using our ensembling approach, in this case, again, using linear mixed effect models, GMRF, which is our method of predicting better in rural areas, and random forest to go ahead and predict daily 1 kilometer PM2.5. And here you can see the different models that we've run, the linear mixed effect model, the GMRF, and the random forest, again, each with its different algorithms and biases, producing slightly different results. And you can see the performance of each of these models, that vary between the models, but by using our ensembling method, in this case, we moved from GAM to use a tensor product, which is another kind of geospatial method of ensembling, taking into account the different predictions from each different model and allowing the predictions to move smoothly over space and time allows us to produce a much better overall performance if you can compare the tensor product approach in terms of the performance, the root mean square prediction error, compared to the individual single models. Finally, Alan Just, my collaborator, has gotten years ago an ECHO-funded OIF, and we started developing these models across the US. And this is soon to be published, but we have these very similar models run across the entire of the US. This is an example of the same model running across CONUS, and this is an example day or example period from December 2018 to November 2019, grouped by season, and you can see the different spatial variability by season across the US. So now let's move over towards air temperature modeling. Another main component in climate change is, it affects obviously air pollution, but obviously air temperature. And why do we actually need to model air temperature? Why not use just the monitors or use some reanalysis data from these large-scale global data sets? We've seen and we've published on this that, you really do need spatial temporally resolved exposures, especially intra-urban, especially in cities where we see a lot of variation street to street, neighborhood to neighborhood. And if you don't have that fine spatial variation, you will run into exposure assessment errors and create exposure bias in your models. And we've seen that weather stations rarely are dense enough in rural areas and cities, like we've shown, with the PM models. And the reanalysis data, even though a lot of them are becoming more readily available, they are very rarely available at sub 1 kilometer, really high spatial resolutions. And even if you want to run these reanalysis data models, they're very complex and time consuming. And that's why we had the idea of implementing the same methods that we've implemented with air pollution, applying some of our kind of remote sensing or hybrid approaches to look at temperature modeling. So we're integrating big data from monitoring networks and satellites. And this is an example of, in New England, we have 26 million observations for 1 year from satellite data. And with LST as opposed to AOD, we can get measurements over nighttime, so we can have different points across the day. And I'll show you an example of how we do that. But this is the first model that we published in 2014, and you can see the spatial pattern of predicted air temperature values here, generated from this hybrid approach using land surface temperature. In this case, this is data averaged over 2011 for the metropolitan New York area. And as you can see, I can't hear the audience as I do in normal talks, but I always ask, can you identify this area? And it's very clearly identified. This is obviously Central Park, and you can see the difference of temperature variability. Mind you, this is aggregated over an entire year. So even long kind of term averages, you can see a degree of 2 centigrade difference. And this is accentuated if we have a extreme, event. We have like a heat, a critical heat day. We can see, 4 or 5, sometimes even 6 or 7 degrees Celsius, depending on different cities of the world, difference between the vegetated areas and the downtown urban core. Prediction accuracy is, again, very good. It's actually, I think, less complex to model air temperature compared to air pollution because of various reasons, because of, the satellite has 4 overpasses, and, this is real kind of, surface level product as opposed to the column level product. So as you can see, model fits are very good. And, of course, when we published this first, reviewers were kind of insistent to check difference between different regions, between the rural and the urban, between different seasons. And you can see the model performs quite well under, very different conditions. And these are some of the examples of, the models that we ran. So we ran this model in France, and this is specifically Paris. And again, model accuracy was very good. We have these models. I'm going a bit fast because I want to, make it in time, but we have these models in different regions of the world, in Italy, in Israel, and Switzerland. And then one of the new things that we did in France was start to apply some of our ensemble techniques and go sub 1 kilometer. So the rationale was that we can apply dynamic modeling because, obviously in cities, we expect a lot of intra-urban variability. But if you go outside to rural areas, depending on, elevation gradients and geoclimatic localized condition, in general, we don't expect variability to be that high. So what we can do in terms of saving computational powers, because these models are becoming more and more complex as we go down in both spatial and temporal resolution, is to have the model dynamically shift where we have high resolution in urban areas and lower resolution in rural areas. So we looked at predicting daily minimum, mean, and maximum temperature in France for 16 years. We applied land surface temperature from MODIS and weather data from Meteo France, the French meteorology agency. And again, we applied this sub 1 kilometer, this 200-meter spatial resolution specifically for areas that we identified as, urban areas, which included 103 French cities. In the first stage, to predict the 1 kilometer air temperature from the satellite land surface temperature, we applied different models, linear mixed effect models and random forest models, and then did the same gap filling approach that I presented in our PM 2.5 modeling. But then to go sub 200 meter, again, dynamically, when we identify populous areas, we used the random forest and gradient boosting approach, and again used a tensor product to combine or ensemble these two different approaches into an overall 200-meter level prediction. This is an example of the 1 kilometer data across France, as you've seen in our previous iteration. But here you can see the difference when you go to, you go sub 1 kilometer and you go to a higher resolution, you can see, or you can get much greater spatial variability. So this is Paris in this case, and you can see that within the city, the different variability between the minimum, the mean, and the maximum temperature. And this is run daily. Performance again was very good in both the 1 kilometer and the 200-meter resolution models. Another thing that we were interested in doing is, as opposed to PM data that again is very hard to get, but very hard to get monitored data at a 1 hour level. Here with air temperature, it's quite easy in different regions of the world to get hourly estimation. So our aim was twofold here. One was to first impute land surface temperature from MODIS, but two, to also generate hourly 1 kilometer estimations from in the calibration stage. So we used both MODIS LST, but also an additional geostationary satellite that only covers parts of Europe and the Middle East called Severi, which allowed us to create these LST surfaces on an hourly level. We also used ERA5 reanalysis data as part of the ECMWF global reanalysis data and additional spatial and temporal predictors regarding to meteorology conditions, atmospheric conditions, and land use. So at the first stage of this model, we took the ECMWF data and the Severi data and to put that in the model. This is an example of the gridded coarse reanalysis data and the satellite 4 kilometer Severi data, and put that in a random forest model, including the ERA5 data, the Severi data set, and managed to use that to impute full surfaces of land surface temperature that we imputed from MODIS. And this is an example of the data from the satellite. As you can see, there's a lot of missing areas daily. With our random forest approach, we managed to predict daily full surfaces of satellite data, which are then can be used as inputs for our calibration stage. This is the performance of our imputation stage. You can see the RIMSEs of the stage 1 imputation stage was very good, which allowed us to move forward and predict air temperature data at a 1 hour and 1 kilometer resolution. Again, we're taking the reanalysis data, the hourly data from the Israeli Meteorology Society, including hourly temperature data, and additional geospatial predictors. And then we run that through a random forest regression, allowing us to end up with daily predictions and hourly predictions in that day across that 24-hour period. And model performance was excellent, again, with RIMSEs of 1.58 degrees Celsius across the study period. Again, through the ECHO initiative, we're now modeling temperature CONUS-wide. So this is an example from a preliminary model showing, again, a specific day across the US. This is, in this case, the 27th of July, 2023. And these are sub 1 kilometer predictions across the US. Finally, I'll take another 2 or 3 minutes. I hope that's okay in terms of time, just to kind of also present that we're not just focusing on air pollution and climate and temperature. There's other kind of related exposures that may have a synergistic effect with these climate change exposures, such as noise estimation models, where we can take or use or apply classic approaches such as land use regression and have a field campaign where we measure noise across a few years using noise measurement monitors, research level monitors such as this. And then by doing that, and doing a field campaign for several years, we can go and predict noise level in different regions. And in fact, we're doing that now in Mexico City. This is work led by Laura McGuinn, now in Chicago University, where we have a pilot study of trying to predict noise across the huge metropolitan of Mexico City. We're also looking at light at night. People that don't know what light pollution is it's defined as the alteration of natural light levels in the outdoor environment owing to artificial light due to man-made sources of light. There have been many global maps created on light at night. This is a map that we created in our lab many years ago, looking at light at night in 1997. And this is the same map that we created for 3 million years ago. This is a joke, of course, but this would be how it looked if we did that, because there was no anthropogenic activity, and the satellite data knows how to clean out wildfires and so on. So we really are getting a representation of the light at night or artificial light at night. This has a lot of biological outcomes, such as disruption of the circadian rhythm. So we're using different satellites, completely VIIRS and DMSP, and we're doing very similar exercises looking at light at night. And obviously we have other satellites that we use, such as Landsat, where we can look at exposure to greenness or natural areas around participants' location. This is an example of how we use these other satellites to look at NDVI, which is a vegetation index showing how green your area is across where we live. And this is the Progress Mexico study, who is led by Robert Wright from Mount Sinai, and using the satellite to address or assess their greenness exposure around their place of residence. And I think I'll stop here and leave time for questions. So thank you very much.
Thank you very much, Dr. Klug. That was a great talk. Always great to see new novel methods and exposure assessments. I think it's so important to getting the accurate description of these exposures in order for us to understand the health effects, which then have great policy and behavioral implications. So yeah, I applaud your work. So if anyone in the audience does have questions, please do put them in the Q&A. And while we wait on that, I did have a few questions of my own that maybe we could start with.
Sure.
So I was impressed with your description of, there's this column measure that you get from the satellites, and you have to calibrate that to get to a ground level exposure. And you have these novel Gaussian methods for doing that. But I was curious if, I guess two things. One, if you're still seeing, you showed the temperature seemed to be really good agreement, but if you're still seeing some, differences in error estimates between urban areas where you have more monitors to calibrate against than rural areas. And two, if you're seeing any challenges based on geographic regions, like you had mentioned, in Israel, some of the dust storms make it challenging, but I'm just curious if you're seeing too, differing model performance based on how geographic area. Yeah.
Well, these are great questions. To start with, yes, I mean, obviously we do see differences between urban and rural areas in terms of performance. We can't, that really depends on, which rural area versus which urban areas in terms of the, the geocharacteristics, the geoclimate, and so on. At the end of the day, we can only validate where we have monitors. So luckily in the US, we have, an external network of monitors called the Improv station that's also kind of semi-operated by EPA, where we can actually go to rural area to validate and compare the performance in rural areas compared to urban areas. And again, it's not, constant. Yes, the more monitors we have in urban areas in general, on average, we're seeing better performance. But through the use, and one of the reasons that we developed this GMRF approach is allow different statistical approaches to better fit these models in rural areas. So we've published in France. I don't know if I've shown that, but in France we actually do compare real performance using GMRF versus, the classic methods that we use, and we see a much higher performance, or more robust performance using the GMRF approach. Now, the second question, remind me the second point that you had.
It was related. So it was just, do you see different, like, are there different geographic areas that present more of a challenge to the modeling techniques,
Yeah,
whether it's, through a characteristic like dust storms or latitude or?
absolutely, absolutely. So for example, in India, I mean, I think there's many challenges. It took us, I mean, I'm kind of, involved, co-leading this huge kind of push in India called the Chair India project, where we spent many years, first acquiring data. So, not in every region you actually have good enough input data to calibrate the models. So we had to spend time in, deploying monitors and acquiring data, but also, India is very challenging in terms of they have like a lot of regions that have very bright surfaces. So we had to kind of go back and forth and adjust the actual algorithm to produce the AOD data. And there's other challenges such as the Himalayas. You have very highly elevated areas, and obviously performance is not going to be as good for many reasons, right? We have a lot of there's monitor sparsity, but there's also challenges of accommodating these kind of specific characteristic in the modeling approach. So yes, I mean performance is definitely not uniform across different regions of the globe.
Hmm. And you had also mentioned one approach too is like the shifting resolution. So maybe using finer resolution where you can, coarser where it's maybe less, not as accurate. But I was curious, since we're talking exposomics here, where we're considering like, combining probably several factors. So if someone was interested in looking at like combined effects of particulate matter and extreme temperatures, what would be the implications if I was, if the errors of those two measures were different and I put them into the same model, if I'm looking at trying to predict a health effect?
That's a great question. In fact, one of the things that we are kind of focused now is kind of, quantifying errors and kind of, model performance, specifically, as you said, under different circumstances. So, this is, model uncertainty, model error is something that's, I think still a challenge and unresolved, not just with us, with, a lot of my colleagues, running these models. And this is something that I think we should definitely kind of, dive deeper. I think we are doing that, collaborating with some biostatisticians to kind of specifically look at that on, per region, per kind of period, per season, model error and model uncertainty, and for the different models that we run, and then how can we accommodate for that in the different epi models that use these predictions.
Mhm. Great. So I don't see any questions in the Q&A, but maybe just for people that are here interested in doing work like this, I'm just curious what software packages you might use or recommend.
Sure, sure. I would start by joking, saying don't, because I mean, we're really like just yesterday. I mean, we're really kind of hitting, I think, a wall, not just us, with, we're going deeper in terms of, spatial and temporal resolution, sub, 200, 100 meter, daily and hourly. We're doing the whole US, and, we have these 5 servers, each one of them is like $30,000, and we're using clouds, and still we're hitting these computational challenges and, modeling challenges. But in general, in terms of packages, obviously, we've been using R, and the different geospatial packages in R, whether it's GDAL or, raster or stars, or, the new package is called Terra. But a lot of my younger students are kind of shifting to Python. So there's a good kind of, a geospatial library infrastructure in Python, allowing to use the same tools that we use in R, but this time in Python, that helps us efficientize and also kind of expand, incorporating new machine learning tools and libraries that are, available only in Python. That's the cool new thing. But that's another kind of resource that we are kind of shifting towards, especially when we kind of, keep expanding the scales of predictions.
Okay, so we have another generational. It used to be R was for the younger people, and now Python is. So we're having more generational
Sure.
differences here. Okay.
I was kind of, critical of my mentors using SAS, and I kind of started using R now. I'm kind of getting the same.
Yeah, it all comes full circle, right?
Yeah.
Um, so one question came up in the chat. It says, please, do we have other models aside from the ones being spoken of? So I assume this might be getting at differing method techniques. I mean, I assume other than what you've been doing, there's other work in the field too.
Yeah, absolutely. So just to be clear, I don't think our models are, I hate these words. They're not like best in class. I mean, there's different approaches, and I think every approach is valid. There's very strong groups from Emory and University of Washington and Brown and Harvard and so on. I think the approaches are sometimes similar but also different. Each model has its strengths and weaknesses in terms of performance in different regions and kind of different biases. Some of these hybrid models incorporate remote sensing. Some of them use classic statistical techniques. But there are different models from different groups that predict PM2.5. Again, there's a lot of strong kind of groups across the US, and some of them are publicly available. Ours will be when it's done. It's not published yet. Some of them are not, so that depends on But I think mostly a lot of these groups are very open to collaboration. So just approaching different groups via email, I think would allow you to kind of have a better grasp of what they do and what exposures are available and so on.
Okay. So it doesn't look like we have any more questions to go. So I just want to thank you again for your time, and I want to thank everyone here for joining our webinar today. Just a note that webinars, this will be the last webinar of 2024 from the Here Exposomics series, but it will be continuing again in 2025. So you can be on the lookout for emails or social media announcements, but you can also check hereprogram.org and get a list of upcoming webinars that are planned in 2025. So again, I appreciate everyone for being here. Thanks for joining us, and we'll hopefully see you again in 2025.
Thank you.